welcome you all to this first talk of the fourth workshop in Fluids and PDE. I won't give a more formal welcoming now because there will be such a thing later tonight with a cocktail. But I do have a few announcements before we start with Professor Bardos' talk. The first announcement is, Elena, please help me out. Registration will still be open all day today and further on if you so need. The dinner, payment for the dinner will start this afternoon. The conference dinner you have to pay here sort of so that we'll make a reservation for dinner on Wednesday. And for the sugar loaf visit, well, first you only pay for it there. You just have to sign up so we know how many people go on the bus. But you only pay for it there, and that's also contingent on weather. So we'll have to find something. If it's really raining hard, we'll have to find something else to do on Wednesday afternoon. But I'm sure we can find something. Rio's got many choices. So, to get our conference going, the first speaker of this morning is Professor Claude Bardos from Laboratoire Jacques Willion, and he'll be talking about viscosity solutions and wild solutions. Thank you.
Okay. I think I have a micro. It works? Is it turned on? Yes. Yeah. Okay, so thank you, the first speaker of the morning. I welcome you also. Thanks the organizer to giving me the opportunity to give a talk. Okay, so as the title say, I want to work on this viscosity solution and to try to see what we can learn about the structure of the solution using the wide solution, which were introduced by Camillo Delelis and Laszlo Székely. And it's a joint work with Laszlo, Emil and Edris. Two of them are in the audience, of course, so if they can complain if I don't say what they want. So that's the Navier-Stokes equation, you know, and I won't spend much time on that. I just want to tell you my personal belief, which is at present progress on the Navier-Stokes without constraint on the size of the nu, that will lead to new result on the Euler equation. And I believe that if you don't have a better understanding of the Euler equation at the present state of our knowledge, there is no hope of getting the Clay Prize, for instance. And so what I want to do, I don't want to discuss the issue of the regularity. Maybe someone in the audience in the future will get the Clay Prize. But so I assume everything is smooth. But I claim that even if I assume everything is smooth, there are a series of problems which are still completely open or partly open and which really need to be understood. And in fact, if you read what I wrote for the first four things, I want to insist on what we could say about initial data with Arbroath, what would happen for when u tends to 0 with boundary or without boundary, and with boundary even when everything is smooth and it's largely open. And then you can play combining the two effects, look at large time behavior. There are a lot of other problems, but I don't want to. Don't intend to touch them. And as I said at the end, I want to consider only issue 1 and 2 using simple example and using the dissipative solution and using the notion of wild solution. Okay, so the Cauchy problem, just one word about the Cauchy problem. For the Euler equation, it's well known when u0 is in C1 alpha, 1 and alpha, or in the corresponding sub-F spaces where you have the good injection. That's back to Liechtenstein. It's well posed in 2D with the vorticity in L infinity. And moreover, for smooth solution, I will use and keep in mind that one has the energy conservation. Not big news for this audience. Just one word about the C1, because I will play with this example. at some point, C1 alpha seems really to be a threshold in the sense of well-posedness. Namely, it's contained in the theorem of Liechtenstein, but then with Edris we used a very simple example, which is the 3D shear flow. You look at solutions which are the form U1 of x2, U3 of x1 minus t, U1 of x2 and x2. This guy is obviously divergence-free. It solves the Euler equation, and you observe by the chain rule that the derivative with respect to x2 will be t times the derivative with respect to x2 of u1 plus u3 of x1 minus t u1 of x2 and x2 plus this one which play no harm, the derivative of u3 with respect to this second argument. What creates a difficulty is this, the product of these two things, which is here only when t is strictly positive. And that leads you to the conjecture that the thing may immediately become bad. And what we found out just computing the chain rule is that if U0 is in C1 alpha, then the solution remains in C1 alpha, and that's just Liechtenstein. Now, if you take less regular initial data, just compute, like in elementary calculus, you find that the solution will be in C0 alpha. You can construct solution that will be in C0 alpha square. Alpha square is much less than alpha, but not in C1, not more in C0 alpha. So the problem is not well posed in the sense of Hadamard. And it seems that C1, according to a rumor of Edris, will be really a threshold for singularity. Namely, some people may have proven that you can construct different 3D data in C1, so initial data in C1, so that the solution will be out of C1 immediately. Okay, so that's the situation. Now, the next thing, since I want to deal with weak solution, I introduce the notion of weak solution, which is just you integrate by part, multiply, and then you use test functions which are smooth. Basically, you have two formulations that you can use. One, when you keep the pressure, but in the right-hand side, your gradient of phi, then you take any function phi. Otherwise, in the next line, you take function phi, which are of divergence free. And if they are of divergence free, you get rid of the pressure, and you can replace the same equation by the line which is just below, where you introduce what is the Euler solution. So these guys are well-defined weak solution. Now, the striking thing about weak solution is that Schaeffer observed in 1993, and Schnirelmann cooked that in 1997, that you have weak solutions which are of compact support in time. They start from 0, and even after that, they come back to 0. And obviously, they are not physical. One argument, which is an argument I brought from Villani, if there will be physical starting the motion from nothing, that will solve the energy crisis. So they are not physical. So, okay, we could discard them. Now the situation becomes more complicated because if you look formally, for smooth solution, you have the energy conservation. Then there is the idea of introducing a notion of admissible solution. So admissible solution will be weak solution, as in the previous slide, and I just ask as a requirement that they are more physical in the sense that if I put some energy at time 0, then there will be energy at time t, which will be less or equal to the energy at time 0. So that will be a definition, according to Delelis and Zerkedeli, that will be what they would call admissible solution, weak solution with the energy inequality. Then there's a third notion, which I intend to use, because it's very convenient for the thing what I did, which is very close to the other one, is that the notion of dissipative solution. How you get a dissipative solution? To get a dissipative solution, you take a test, any test function W. any test function W which E belongs to D. It's as smooth as you want, and now it's in the whole space. And its divergence free equals 0. It's not the solution of the equation. So even if you take the Euler projection of W nabla W, which gives the term gradient P of W, there is no 0. There is a term on the right. Nevertheless, you take the difference between a real solution, smooth, and this guy W. You take the difference, multiply by part, use the standard trick that you always use for Navier-Stokes Euler, and when everything is smooth, you obtain a formula which bound U of x and t minus W, the L2 norm, by the norm at time 0, which is U of x and 0 minus W of x and 0 squared, the L2 norm, plus an amplification factor, and also a term which comes from EW, which is 2 times the integral from 0 to t, the integral of omega that multiply U minus W, and always with the same amplification tensor. This S of W is the symmetric class of gradient of W plus gradient of orthogonal of W, which is a symmetric matrix, with the my formula that should be divided by 2. Maybe there is a misprint. So what's important to observe here is that you have a definition where no regularity on U is required. You just use the regularity of W here, the regularity of W here, which comes from there, and back here. So it's a definition you can write for someone which is L2. Okay, so far so good. Now, then there is a proof of Delelis and Sekedeli, which I want to recall because I will use that in the case where there is a boundary. There will be a slight difference. I want to recall the proof because I want to believe the difference, and it goes that way. It says that any admissible weak solution is a dissipative solution. Any admissible weak solution is a dissipative solution. Now, what you do for that, you write U of t minus W of t square minus U0 W of U0 square. Expand. The first term is ut square minus u square, and the other term at w square minus 2uw minus the integral of the same value at the time 0. So you can write this relation as you forgot these two first terms, ut square minus u0 square, which means that this equality becomes an inequality, and this difference you use the integral of its derivative. So far, so good. Now, this term, the main observation is that this term is linear with respect to u. The only bad guy will be u, the rest is smooth, so you can, in fact, do the same thing as we do with the Euler equation. When or Navier-Stokes, when you deal with test function, you expand. This is equality, this quantity. That you obtain by an integration by part, which you have to do, which is not trivial. And at the end of the day, you obtain u0 square minus w square plus 2 times the integral of uw s of w plus the integral from 0 to t of the scalar product of e of w minus w. And here, this is the end of the proof. You can just apply the Grunwald lemma. So I have decided that, and if I go back, in the absence of boundary, any admissible weak solution is a dissipative solution. Now, the problem, there can make several remarks. First, that the dissipative solution is a good thing, because if there exists a Lipschitz solution, or only if its stress is bounded, then it will coincide with any dissipative solution having the same initial data. In fact, it's a theorem which compares strong solution with weak solution, as that was introduced by Diperna and Lyons for hyperbolic system already a long time ago. And also that the notion of dissipative solution is stable under strong L2 perturbation of the initial data. If U epsilon 0 converts to U0, then I have still a dissipative solution. I need the strong convergence here. Okay. Now, the stability of dissipative solution does not imply that any weak limit of an admissible solution is an admissible solution. The reason is that the weak limit of the tensor product U epsilon minus tensor U epsilon is not or may not be equal to the weak tensor product of the weak limit, even if you apply the Leray projection of this guy. And this guy is called the Reynolds stress tensor. It is non-negative symmetric tensor. It measures the defect of the strong convergence. And I just want to say for further use and for other talk that may appear this week, first, that it appears in statistical theory of turbulence because the average, whatever average mean of the tensor product, may differ from the tensor product of the average. And it turns out that in recent paper of Tristan is here, Buckmaster, of Deleli, Sekedeli, all this group, this thing which is very physical plays a role in proofs even for equation solution which may not be physical. May not be physical, that's what I refer as one of the basic theorems of Delelis and Sekedeli, which I feel more important than the previous result of Schaeffer and Schnirelmann, and they say that you have an infinite set of rough initial data. You have an infinite set of initial data. They cannot be smooth. They have to be weak due to the weak and strong stability result, but there are the infinite set of rough initial data, say only with U0 in L2, which admit an infinite set of dissipative solution with the same initial data. Admissible, weak, dissipative, infinite set, which means many. Okay. Now, that means that among this infinite set, there will be a natural need for a ruling out, the term ruling out from Edris, discarding solutions which are not physics. Find a criteria that would, among all these admissible or very admissible solutions, there will be a criteria. And I want to compare, in fact, before going on, I just take 2 minutes on this slide to tell you that it's not that was an issue that existed in the air for already many years, not for the incompressible, but already for the 1D compressible. For the 1D compressible, it was found out, and I think it's Peter Lax, that there is a good notion which is the decay of entropy. Now, this control of decay of entropy turns out to be a good criteria if you have small shocks. Whenever the shocks become large, you have examples where the decay of entropy does not imply the uniqueness. Then came another idea, which is due to typing view, which says that you have to introduce a notion of maximum decay of entropy, and hopefully maximum decay of entropy will be a ruling out criteria. Solutions that do not satisfy the maximum decay entropy, you should discard them. Well, that's not enough, because there's an example of Dafermos in 2012 where Dafermos observed that if you take a large shock, so solving the shock is just solving the inverse mapping theorem. So you know that if you have a constant state, solution of 0, then near this state, you have existence uniqueness of whatever you want when the problem is well formulated. Not true when you increase the thing. Now, this inverse inverse mapping problem in the case of the shock can be made very explicit. You can, and if you have a large shock, an example for the isentropic equation, you can construct solutions for which, on one hand, you will have large shock, and you will have a solution which satisfies the maximum decay of entropy. You can also solve, in this case, the corresponding Navier-Stokes, take the viscosity limit, and you pick another shock which is not the same. So this is not a criteria. Now, this is a defect which appears because they make a large shock. To compare with more recent result, I will say that in the more recent result, people have exported that to more than 1D, and in more than 1D, instead they're looking at large shock. It will work for large shock. They just accumulate oscillation in a more clever way, and there is a big family working on that, which is written down there. Okay, so that's where we are. Now, I want to explore the viscosity limit. So to explore the viscosity limit, we observe that's a very simple example, that if you take the shear flow, the basics, the most stupid one, something which goes like that, something which goes like that, with a discontinuity here, not different, they may not be the same. There may be also horizontal boundary value, then you will get a viscosity limit. Now, if you take exactly something which goes like 1 here, and -1 in this direction, then there is an explicit example of then an explicit construction of last law on which he proved that for such initial data, there is an infinite set of admissible weak solutions. The problem in their strategy of constructing weak solution is first to construct a weak sub-solution. And when they have a sub-solution, they can increase that adding oscillation to make it a solution of it. But then you have, on this example, you have a convincing explicit example, not by bare theorem, on which you say that you will have an infinite set of solutions. Now, they are dissipative, and among them, there are an infinity which both conserve the energy and also decay the energy, whatever you want. And this is an example which is written in 2D. You can extend that, we observed that with Edris and Emile. You can extend that by introducing a 3D, a third component, to make it 3D. That's not a big deal. And what I will use just after that is that you can make the same consideration for a rotating flow. You take a disk, you take an initial, I don't want to have problem with 0, so I take an annulus like that, and in this annulus I take an initial data which rotate at constant velocity. It is a standard stationary solution of the Euler equation. Now, if it has a jump on one of the circle in the density, there's a jump here, constant jump, then from that, looking at Riemann problem on both sides, outside of this circle, you can construct an infinite set. You can construct a sub-solution, and from this sub-solution, you have an infinite set of weak solutions. So far, so good. And there the formula, you look rather at the picture than the formula. Okay, now, in the absence of boundary, I start from the energy estimate, and I need a viscosity limit. And first remark, I have this energy inequality. That should be an inequality if you are a follower of Leray. Assume an inequality. You less nu going to 0. Then you observe that in the whole space, it is a dissipative solution. It may not be an admissible solution, but it's a dissipative solution. And then, in this case, as I said already, there will be, in the set of admissible dissipative weak solution, there will be necessity of a ruling out criteria. What is striking in these two simple examples is they are both. It's a very simple calculus to prove that for both of them, you can take Navier-Stokes, look at Navier-Stokes, let the viscosity go to 0, and when the viscosity goes to 0, it converges with this thing. So at least on this simple example, I have shown to you that the viscosity limit is a selection criteria. And I think even if it's a simple remark, it should be kept in mind. And then, when you look at another simple observation which I want to make, it as follows. If you look at the literature on turbulence, there are two things which appear all together. One is that the solution may not be regular, that there is a threshold of regularity in C0 alpha for alpha roughly greater than 1/3, the solution of Euler conserves the energy, and for alpha less than 1/3, for alpha there exists, and that's more recent of Tristan and other people, there exists with alpha, maybe not exactly 1/3, but something smaller, there exists infinite set of Euler solutions which do not conserve the energy. Now, you have this idea of a threshold, 1/3, and you have the idea, and you have the idea of this threshold, and you have the idea of a dissipation. And then a dissipation of energy for deterministic solution will mean you look at nu time, the integral from 0 to t of the gradient of nu square. And you look at this quantity. If everything is smooth when nu go to 0, then you have no anomalous dissipation of energy. If it goes to a quantity which is strictly positive, it goes to a quantity which looks like epsilon, and this type of epsilon which appears in the formalism of Kolmogorov. And I want to show you on this slide, it's a very simple example, that if the limit is regular in the sense is like the alpha is, if the dissipative solution U bar limit is uniformly in alpha greater than 1/3, then you would have dissipation of energy. And it comes first from the inequality of the energy, it's very simple, and then from the fact that the inf limit of the integral of u square x is always greater than the L2 norm of the limit. And the L2 norm of the limit, if this guy is in C0 alpha, will be equal to the initial data at 0. So you compare the second line with the first one, and you see that this goes to 0. I wanted to show that because it's a very simple example where you see the Onsager principle. By the way, CET, many people know that. That means Constantine, Edris, entity. No, Constantine, Laius, Constantine A, Weinan A, entity. Excuse me for that. Weinan is not in the audience. Constantine, it's tempting to say Edris entity. Constantine, Weinan A, entity. And I say it's a simple illustration of Onsager's conjecture that we would like to take on. Okay. Now, I just want to add that this discussion makes sense only in the absence of smooth solution. Otherwise, if there will be any kind of C0 alpha on the sequence of U nu, it will converge strongly, it will converge to a dissipative solution, and therefore, since it will be a dissipative solution, there will be no anomalous anomalous energy dissipation. And in the meantime, just to complement that, this point has to be connected with the last one. So science, I don't see really a threshold when I have uniform Euler 0 alpha regularity in the sequence. It may be important to try to construct solution of Euler that will be limit of solution of Navier-Stokes with viscosity limit, but staying uniformly bounded in C0 alpha. There exists already a solution of Euler in this type of space, which do not conserve the energy. It will be challenging to find one of them, try to adapt the construction so that this guy will be also a viscosity limit of solution of the Navier-Stokes. Okay, I move on for that. And I just wanted to add more remark about the Kelvin-Helmholtz. What I call the shear flow is just remark because I mentioned these two guys. What I call the Kelvin-Helmholtz equation is a flow for which you have, there is the R2, there is the time, and the vorticity lives on a boundary, on a surface, or it's a density which lives on a surface in the space-time. And what's known about that this configuration should be formally equivalent to the Birkhoff-Rod equation, but then, and it was observed by Sigivou, with here Duchon, Robert, Lebeau, that such a phenomena is very unstable. Why it is unstable? It's unstable because it's proven that it's analytic here, and to have the analyticity, you have to start from something which will be analytic at 0 with compatibility conditions so that the analyticity remains. So it's something which is very unstable. Now, just discussing about the instability, I cannot omit to say that it is used in numerical experiment, it is used in the physical literature as a good example. And also, it's more or less one can apply the Euler theorem to prove that if you start from initial data for Navier-Stokes, close to this one, make the convenient hypothesis, then you will have the solution will converge to the solution of Navier-Stokes will converge to an Euler equation, but it's not proven nowhere, even in the case where it's analytic, it's not proven that it will be the Kelvin-Helmholtz. That's a problem we still open. And if you make just a very discrepancy in the analyticity, you start at time 0 with an interval like that. That's a picture of the density of vorticity at 0. Vorticity at t equals 0. You start by this one, which has a small singularity on both sides for the density of vorticity. Then there is an example which is called the Prand-Munt vortex, which has been really worked in detail by Enna, by Milton, by Zuping-Jin. And for my discussion, what you observe is that this example of a Kelvin-Helmholtz, so it's not analytic due to this, and generate by Birkhoff-Rod a solution which is not solution of Euler, which is not a Euler solution. So then, just this slide is to insist on the need of a better understanding of what will be the viscosity limit. And in this spirit, what I explained to you is these two fixtures, is that the Kelvin-Helmholtz shear or rotating flow give the first example of initial data generating dissipative wild solutions. They are wild because you can construct many wild solutions, for which you can rule out the wild solution by the viscosity criteria. And one of the problems on these two examples which maybe should be doable, is to try to modify slightly them if you can look at solutions where you will have some perturbation of the geometry and still both have the viscosity limit and have the existence of many wild solutions. So far, so good. Okay. And I just add this remark referring to a paper which I did with Edris and Lynchitz. This is that the notion of stability is not unique. If you think about stability as regularizing the equation, you can find a fancy way of regularizing the equation, which they call the alpha regularization. And for this setting, the Kelvin-Helmholtz, even the Birkhoff rods, turns out to be stable. So just to insist on the fact that the room around the notion of stability to try to see what we want. I still want to advocate that viscosity will be the most reasonable, but I wanted to quote that. Okay. You can also change this density into a density in a layer, and when it's a density in a layer for Euler, you still get stability. Okay. Now, the next thing I wanted to try to convince you is that the most important thing, from my point of view, in this business are the boundary effect. So, in the presence of boundary, I want to define the Euler equation with no un of x equals 0 on the boundary. And the point, I want exactly to do the same thing as I did before to define what would be a dissipative solution. I didn't get too much of the detail saying that, I gave some of the details telling to you that an admissible weak solution was a dissipative solution. However, there was in the process of establishing that in the whole space a series of integration by part. Now, if I consider the problem in a bounded domain, I want to use this notion to compare with solution of the Euler. And the Euler equation have the bad property for this thing of having solution which have a non-zero tangent component on the boundary, which means that the derivation which I have shown to you in the whole space ceases to be valid in the present case. So if it's not only ceases to be valid, but we had an example which we did with Sekeli and Wiedemann, where we proved that admissible weak admissible solutions are not dissipative. And that's an example which I can just explain on the picture. In fact, to build it, I restrict the domain to this half space in the exterior. Okay, so if I just restrict it to here I have the rotating solution, which is smooth. Since it is smooth, if there is a dissipative solution, that should be the same. Now, the next observation is I construct in all the domain an infinite set of dissipative solution using the notion of sub-solution. What is important, there is an improvement given by Delelis and Sekeli in one of their papers, which is that it's enough to have something which is strictly a sub-solution in a subdomain. So it's enough to readapt the previous proof, which I didn't do in detail, and use this part of the domain to construct an infinite set of sub-solutions. So if I do that, I have generated, thanks to the boundary, I have generated an infinite set of sub-solutions. And since I know that there is only one, that there is a one smooth solution, which is the rotating flow, obviously, by my definition of dissipative solution, I have generated an infinite set of admissible solutions. And since I know that with my definition of dissipative solution, that there is uniqueness between weak and strong, that means here that that means that it is not enough to be weak and admissible to be dissipative. Otherwise, they should consider it. So there is a gap, but you can fill this gap very easily. It's a theorem which we prove with the same type of people. If you assume that there is just, that's omega in R2, there's just a little amount of regularity, a C0 alpha, whatever alpha may be, then you prove that your admissible solution is in fact a dissipative solution. Now, I want to say some comment on the proof, because that will introduce the last topic I want to deal on. This proof is improved by using a trick of Cato, which was published in a very obscure paper in a proceeding of Berkeley, but which became now very popular in our community. The idea is to prove this relation, the integration part, which I did, which is valid, believe me, when you are in a bounded domain, when the W is the intercompact, to extend it to guys which are not in bounded, which have a support which may hit the boundary. So what you do, you just make an approximation. You observe that since the local property, you look at the voisinage of one point, you construct a corrector in the style of, so it's local, it's the curl of a psi. The curl of psi you multiply by someone which is 0 on the boundary and not 0 in a small neighborhood of order epsilon of the boundary, which is defined by this formula with the epsilon here. Put it in the equation. So since it has compact support, everything works. Let epsilon go to 0. You recover the equation. So it's important that says that you need the C0 alpha to ensure that admissible solution will be dissipative, will give you the criteria of uniqueness. Now, I want to go on. To go on, I will look at maybe more general boundary condition. I don't want you to copy that, but basically, this is a most natural one. When lambda, for Navier-Stokes, when lambda of nu is infinite, it gives Euler, it gives Dirichlet. When for different type of functions C, you can replace that as a condition on the symmetric tensor or a condition on the antisymmetric tensor. It's a maybe pedantic way to write all the natural boundary conditions of Navier-Stokes. All of them, they give an energy inequality, which for nu equal to 0 recover the standard one. So now I am dealing with the notion of convergence of solution of Navier-Stokes, knowing that there is an energy inequality. And I want to prove that at the limit, it is a dissipative, and I insist on the word dissipative, solution of the Euler equation. Okay, so I redo the same computation. I multiply by, take the difference between a test function, which is not 0, multiply by u nu minus w, turn the crank. I obtain everything before, except on top of that, there is a term which is nu time d nu over w, because the w at the limit is not 0 at the boundary. So I write it for 2 minutes. It's nu time. The crucial term will be nu time du over dn, and it's just its component, tangent component, which is important because w is tangent to the boundary. So that's the guy, and then there is a very simple criteria which is with the Grandval lemma. I turn the crank, I write the thing as you see, and I obtain that if nu du d nu goes to 0 in a very weak sense, because I have freedom to take the W smooth, which means I take the limit from 0 of t of du d nu sigma against a smooth function d sigma dt integrated on the boundary. If this goes to 0, then the limit is the smooth solution if the smooth solution exists. And in particular, with my fancy boundary condition, if lambda of nu goes to 0, the limit will be a dissipative solution. So this criteria is very simple. It has not been observed. I don't know why it's not so popular in the literature, but I claim it as a small generalization of the criteria of Kato, because the criteria of Kato says that if I look nu time, the integral from 0 of t of the vorticity on a layer of size nu, if this goes to 0, then the limit is the smooth solution, in presence of a smooth solution for the Euler. Now, I just want to show you that I can get that directly from, I can get directly this relation from the Kato criteria, just to show the consistency of the thing, and it goes that way. Once again, you construct a corrector, but you can construct the corrector in the spirit of the Kato corrector with something which will be 0 on the boundary, put it in the equation, turn the crank, put it in the Navier-Stokes, just use the Navier-Stokes, whatever the boundary condition will be, use the Navier-Stokes. The bad term, in this balance of quantity, you have two terms which are important, only the integral on d omega of nu du d nu w, and the integral of u nu tensor nu w, gradient of w. And the second with something which goes to 0 depending on the boundary condition, and the sum to this term will go to 0 because you have constructed a corrector which is in the size of nu. You have 2 or 3 minutes more, and this will tell you that this will tell you that this quantity goes to 0. So it's not a surprise. That's what I said. And you can just say, compare the criteria of tending to 0, this quantity going to 0, the strong convergence, the weak convergence, the convergence in a layer. It's the same thing. Now, I have also, once again, the same consequence, which is due to the fact that any admissible solution which is in any C0 alpha will be a dissipative solution. In this situation, if I have a smooth initial data, you don't see the threshold. The threshold of regularity 1/3 is visible only if for non-smooth initial data. One more line, that's what I said. And just so just one and said, so that's just one more comment, is that, of course, the Kato criteria is completely compatible with, not in contradiction with a Prandtl ansatz, because if a Prandtl ansatz is valid, it's parabolic, you can compute this quantity just with the dn of nu, which will be, the gradient will be of the order of the square root of nu, and this goes to 0. So it's not in contradiction with the series of results, Asano, Kaflish, San Martino, Canone, who prove the validity of the Prandtl and the convergence, but only for small time and smooth initial, and very, very smooth, in the sense like Kelvin Helmholtz, analytic initial data. Okay. That I will skip. And just one remark, just to come back to this criteria. Before preparing this talk, I tried to look at papers of people that may be here around. Some of them are here. And I found out that this condition, which is not very present in the literature, it appears somewhere in a paper of Konstantin, Kukavica, and Vikol, and just since I don't have time, I want to not elaborate, but they say it's a formula 1/8 in the paper, and that will be interesting to make the connection between this, which is my favorite notion of convergence to a strong correlation here, and what they have in their paper. Thank you. Exactly on time, Chairman.
Hello.